So yesterday we have completed the Henry's law. What is Henry's law? The solubility of a gas in liquid is directly proportional to the the partial pressure of the gas in liquid. Now, as today I told you, we will do the numerical today. My question I have written here. Oxygen is bubbled through water at 293 Kelvin. Assuming that oxygen exerts a partial pressure of 0.98 bar, calculate the solubility of oxygen in gram per liter, and kh for water is given. Now, what is Henry's law? P of oxygen is equal to kh into mole fraction of the gas. Now, partial pressure of oxygen is given. P is equal to 0.98 bar. Then what kh is given? It is 34.84. kh is equal to 34.84 kilobar. Kilobar, one is in bar and the other is in kilobar. You convert this also into bar. That is 34.84 into 10 raised to 3 bar. 10 raised to 3 bar. Now both are the same unit. Now from this kh is known, partial pressure is known, you can calculate the mole fraction of the gas oxygen. So x of oxygen is equal to P of partial pressure of O2 by kh. Now what is partial pressure of oxygen? 0.98 divided by bar divided by 34.84 bar. Now you will get an answer. Now what is this x of oxygen? Mole fraction of oxygen. X of oxygen is equal to number of moles of oxygen by number of moles of oxygen plus number of moles of water, because oxygen is dissolved in water, and you will have to find out the weight of solubility of oxygen gram per liter. That means we have taken 1 liter of water. So you will have to find out the number of moles of oxygen dissolved. Then only you can find out weight per liter, isn't it? So number of moles of oxygen you can find out from mole fraction. Mole fraction of oxygen is equal to number of moles of oxygen by number of moles of oxygen plus number of moles of water. Now number of moles of water is much higher in quantity when you compare with the number of moles of oxygen. So we can write it as here number of moles of oxygen divided by number of moles of water. That is equal to so x of moles, we got the answer here. Now number of moles of water, how will you find out? See, water is 1000 liters, sorry 1 liter or 1000 milliliter. So weight of 1000 milliliter of water is 1000 gram. So it is number of moles of water is equal to water. It is equal to 1000 divided by 18 and is equal to 55.55. So you know the number of moles of water. Then how it is number of moles of oxygen? Number of moles of oxygen is equal to mole fraction of oxygen into 55.55. So you can find out number of moles of oxygen. If you know the number of moles of oxygen in 1 liter, you can find out its weight per liter. How? Weight per liter is equal to number of moles into molar mass. Number of moles you will get from here. What is molar mass of oxygen gas? It is 32 gram. So that is equal to number of moles of oxygen into 32. So you will get weight per liter or gram per liter. So this is how you do it. So partial pressure is given, then kh is given. You can find out the mole fraction of the gas, that is here it is oxygen, and one is given in kilobar and the other is in bar. You convert the unit, then you have found out mole fraction of oxygen. Now mole fraction of oxygen is equal to number of moles of oxygen by number of moles of oxygen plus number of moles of water. When you compare number of moles of water with the number of moles of oxygen, number of moles of oxygen is very less. So we take it as sum, will take it is almost equal to number of moles of water. So that is equal to number of moles of oxygen by number of moles of water. What we will have to find out is number of moles of oxygen. Number of moles of water is equal to, it is in 1 liter. So 1 liter means 1000 gram by 18 will give you the number of moles of water as 55.55. 1000 by 18. And what is now number of moles of oxygen? It is mole fraction of oxygen into number of moles of water, that is XO2 into 55.55 will give you number of moles of oxygen. If you know number of moles of oxygen, you can find out the weight per liter, that is into molar mass of oxygen gas, it is O2. So 16, oxygen atomic mass 16 into 2, 32. So it is molar mass is 32 gram per liter or gram per mole. So when you multiply, you will get the weight per liter. Okay. So this is how you calculate the number of moles of oxygen gram per liter. Vapor pressure. It's not a new term for you. Last year you have studied what is vapor pressure. Now what is vapor pressure? See, when a liquid is kept open, what will happen? Evaporation will take place, and evaporation is a surface phenomenon. From the surface, the molecules of the liquid, they get energy by collision and to escape from the intermolecular force of attraction. Then they goes to vapor state. Then this rate of evaporation goes on, and when rate of evaporation goes on, the reverse process, that is condensation also will take place. So rate of evaporation goes on decreasing as surface molecules decreases and rate of condensation goes on increasing. At some point, rate of evaporation will become equal to rate of condensation. Then we say that equilibrium is reached. Equilibrium is reached, and whenever a vapor is there above the surface of liquid, the surface of the liquid, the vapor will exert a pressure on the surface of the liquid, and it is called a vapor will always exert a pressure on the surface of the liquid. Now when the equilibrium is attained, the volume, so the pressure exerted by so as the rate of evaporation will increase, then rate of evaporation will decrease and rate of condensation will increase. At certain point, the rate of evaporation will become equal to rate of condensation, and we said the equilibrium is reached between the liquid and the vapor phase. Then the pressure exerted by the vapor on the liquid surface at equilibrium is called equilibrium vapor pressure, or simply vapor pressure. So vapor pressure is the pressure exerted by the vapor over the liquid surface at equilibrium. Which equilibrium? Liquid in equilibrium with the vapor phase. Okay. So when liquid is kept open, it will start to evaporate. And at the same time, condensation also will take place. Molecules, when they go up, when they collide, they will lose energy and they will condense and come back to the liquid surface. And these two processes, that is evaporation and condensation, both are simultaneous. So at some point, what will happen? Rate of evaporation will become equal to rate of condensation. Then we call that equilibrium is reached. The pressure exerted by the vapor at equilibrium on the liquid surface is called equilibrium vapor pressure. Now, this vapor pressure has a lot of role to play. See, whenever the vapor pressure of a liquid become equal to atmospheric pressure or surrounding pressure, then we say that the liquid will start to boil. So we studied boiling point is the temperature at which a liquid start to boil. Now, what is boiling point actually? It is the temperature at which the vapor pressure of the liquid become equal to atmospheric pressure. Understood? Or the surrounding pressure. That is why in a cooker, when we close it and heat it, what happens is to temperature to make inside the pressure is very high. This pressure to become equal to atmosphere, the surrounding pressure. The liquid is inside the cooker and above that pressure is very high. So the liquid boil only when the pressure or vapor pressure become equal to the surrounding pressure. Surrounding pressure means surrounding pressure of the liquid. That is very high. So that means the liquid will boil only at a high temperature. So water, if you are taking in a cooker and you keep things to boil, what will happen? Water will boil only at a high temperature and food will be easily cooked. Understood? So this is how what is boiling point. So vapor pressure, it is the pressure of the vapor. Now my question is, suppose we are dissolving a non-volatile solute in a volatile solvent. Suppose you are adding sugar in water, or you are adding salt in alcohol, etc. What will happen to the vapor pressure of the solution? Now it is pure solvent. Water is a pure solvent. In that you are adding salt or sugar. What will happen to the vapor pressure? See, I told you vapor pressure is a surface phenomenon, isn't it? It is a property of evaporation is a property of the surface molecules. So when the evaporation, when it was a pure liquid, water was a pure liquid or whatever may be, it was a pure liquid, the surface molecule is fully occupied by the solvent molecules. No other molecules are there. Now you added an non-volatile solute. What do you mean by a volatile solvent and a volatile non-volatile solute? Volatile solvent is a solvent which easily vaporizes or it vaporizes. If a substance is not vaporizable, we call it as a non-volatile. Sodium chloride is non-volatile. It is a non-volatile solute because you keep it open, it will not become vapor. But if you keep camphor, it will become vapor, isn't it? It is a volatile substance. So volatile substances or solutes are those which will not become vapor if you keep them exposed. So here we are going to add a non-volatile solute to a volatile solvent. So in volatile solvent, pure solvent, if you take, the surface molecules will be fully made up of the volatile solvent molecules. Surface solvent molecules which are volatile. Now you are going to add a non-volatile solute like sodium chloride. If you are adding a non-volatile solute, what will happen? The solute molecules will enter inside. Some of the surface will be occupied by the non-volatile solute particles. So before addition, there was only volatile, there were only molecules of the solvent. Now when you added a non-volatile solute, there will be non-volatile solute molecules also on the surface. Then what will happen? Number of molecules which evaporate decreases, decreasing the vapor pressure. So the vapor pressure will decrease when you add a non-volatile solute to a volatile solvent. Understood? Now, all this change in vapor pressure is governed by certain laws. The first is, one such law is Roault's law. Roault's law. Now what does Roault's law states? Roault's law states that the vapor pressure of a solution of a non-volatile solute in volatile solvent is directly proportional to the vapor pressure of the solvent. The vapor pressure of the mole fraction of the solvent. The vapor pressure of a volatile solvent, solution of a non-volatile solute in volatile solvent. The vapor pressure of a solution of a non-volatile solute in a volatile solvent is directly proportional to the mole fraction of the solvent. Mole fraction of the solvent. So let P is the vapor pressure of the component A. We have two components, A and B. B is the solute and A is the solvent. Now PA is the partial vapor pressure, so the vapor pressure of the solution. Then this PA will be directly proportional to XA. PA will be directly proportional to XA. This is if the solute is non-volatile. Now if the solute is volatile, then the vapor pressure of that component also will be directly proportional to its mole fraction. Suppose we are taking two components A and B. Both are volatile. Both A and B are volatile. So, both PA will be directly proportional to XA and PB, that is that component B. Vapor pressure of the component B will be directly proportional to XB. So, we have taken two components A and B. First we talked about one volatile and other non-volatile. If one is A is volatile and B is non-volatile, then the vapor pressure of the solution PA will be directly proportional to the mole fraction of the solvent, that is XA. Then we have seen. Now in the next case, if both the components are volatile, both A and B are volatile, then PA will be directly proportional to XA and PB is directly proportional to XB. Then what is our total vapor pressure? P total is equal to PA plus PB. Isn't it? Now what is PA? If P naught A is the vapor pressure of the pure solvent and P naught B is the vapor pressure of the pure fraction B. PA is the vapor pressure of the pure component A and PB is the vapor pressure of the pure component B. Then we can write PA. This is directly proportional to XA and this PA will be equal to a constant. Which is that constant? P naught A into XA. The constant is P naught A. P naught A will be a constant because it is the vapor pressure of the pure solvent A. It will not change. So now when you add a component B which is volatile, then the partial vapor pressure of A is equal to P naught A into XA and partial vapor pressure of B is equal to P naught B into XB. P naught B into XB if both the components are volatile. Now, according to Roault's law, the total pressure P is equal to PA plus PB, the sum of the partial pressures of the components. So, P is equal to PA plus PB. Last year we have studied Roault's law. That is, total pressure is equal to the sum of the partial pressures of the components. So, P is equal to PA plus PB. That is equal to P naught A into XA plus P naught B into XB. So, PA is P naught A into XA and PB is P naught B into XB. So, total pressure PA will be equal to P naught A into XA plus P naught B into XB. And you have seen mole fraction of two components XA plus XB is equal to 1. Then what is XA is equal to 1 minus XB or XB is equal to 1 minus XA. So instead of XA you can write 1 minus XB or instead of XB you can write 1 minus XA. So if you know one of the mole fraction, so P naught A into XA plus P naught B into 1 minus XA. 1 minus XA. So this is Roault's law. Roault's law has two conditions. One is if one component is volatile and other is non-volatile. A is volatile and B is non-volatile. Non-volatile. So A is volatile and volatile component is A and non-volatile component is B. Then PA, the partial vapor pressure of the solution will be is proportional to mole fraction of the solvent A or the part A. Then PA is equal to P naught A into XA. This is if one of the component is volatile. If both the components are volatile, then we can write PA will be directly proportional to its mole fraction XA and PB will be directly proportional to the mole fraction of the component B XB. Now, to change the proportionality sign, the equal to sign, we have to multiply with a constant. Here the constant is P naught A. P naught A is the vapor pressure of the pure solvent A and P naught B is the vapor pressure of the pure solvent B. So, PA is equal to P naught A into XA and PB is equal to P naught B into XB. And according to Dalton's law of partial pressure, so total pressure is equal to sum of the partial pressures PA and PB, that is equal to P naught A into XA plus P naught B into XB, or instead of XA you can write 1 minus XB, or instead of XB you can write 1 minus XA, substitute. Now you find out what is P. Okay, you will have to substitute. See, I already substituted. You will have to find out what is P in terms of XA. Understood? So this is Roault's law. Now if you draw the graphical representation of Roault's law, suppose this is, we start with the XA is equal to 1. The part that is XA is equal to 1 means only one component A is there. Now what happens, this is the partial pressure, suppose it goes on decreasing. It goes on decreasing. So this is PA. This is XA is equal to 1 and XB is equal to 0. I go on adding A, so B component, then we reached here. This is vapor pressure. I plotted vapor pressure. Now this is the partial vapor pressure PA. Now what I do is I have plotted PB. The vapor pressure of B is plotted, and here XB is equal to 1 and XA is equal to 0. That means pure solvent B. I plotted pure solvent, vapor pressure of the pure solvent B, then it start decrease. This is it. So this is PB. Now this will give you PA plus PB. The total pressure PA plus PB at each composition. Okay. So here XA is equal to 1, that is only one component is there. So this will be P naught A. That is vapor pressure of the pure component A. Here XB is equal to 1, that means only the component B. So this vapor pressure is equal to P naught B. So this is the vapor. Suppose B is having higher vapor pressure, then you can draw like this. Suppose this is it. It has a higher vapor pressure. Then P naught B is this one. So this will be our PA plus PB. Okay. So this is Roault's law and its graphical representation. So Roault's law for two different cases are there. One is if one component is volatile and other is non-volatile, and then the vapor pressure of the solution will be directly proportional to mole fraction of the volatile component A. If both the components are volatile, then this is the case, and you have drawn the graph. This is the graphical representation of Roault's law.